Hello everyone, welcome to 2021's TA Workshop. My name is utilised. I'm a senior TA applicant, and today I'd like to discuss with you about sample size calculation. So without further ado, let's go and do that, shall we? So I want to break down this video into three main parts. Firstly, I want to briefly discuss with you about a general overview of how sample size is calculated throughout clinical trials. Secondly, I'd like to comment on why it is important for us to calculate the sample size in a clinical research. And lastly, we will be speaking about the parameters that we utilize and need to consider in order to properly do the sample size calculation. Okay. So let's start looking at the consort statement. So the consort statement from 2010 has a whole section dedicated to how to report sample size calculation, and it's interesting to see that they elicit that for scientific and ethical reasons the sample size for a trial needs to be planned carefully, and we need to balance the medical and statistical considerations at it. If we do a brief literature review on the quality of sample size calculations, we see that there are two main articles that I found. First of all, there was Moher et al., which was one of the first groups that looked at the quality of sample size reporting, and they looked at three high impact journals. They looked at JAMA, they looked at New England Journal of Medicine, and they looked at Lancet, right? So quite a big names, right? And it's you see in it that there were 383 RCTs analyzed, and from those well, this was a study from 1994, so it was quite a long time ago. So if we fast forward a couple of decades, we can see that Charles et al., they tracked 6 high impact factor journals. So there was JAMA again, New England, and Lancet again, but they also added BMJ, Annals of Internal Medicine, and PLOS Medicine. And they looked at from 2005 to 2006. And there were over 200 selected articles, and about a third of them adequately and accurately reported the parameters required for sample size calculation. And even so, it was about a decade later, 5% of them didn't report any sample size calculation at all, right? So there was an improvement, but it's still far from where we would like it to be, right? I don't know about any studies that are more recent, so maybe that's something that needs to be done, or if you are aware of it, please share it with us so we can keep discussing. And if there isn't, well, maybe we can do research about it, right? Now that we've taken a look at the landscape of sample size calculation in clinical trials, let's move on the discussion to why it is important for us to calculate the sample size. So, whenever we are performing a clinical trial, we have to be mindful that even though we're trying to be as close as possible to the truth, we can make mistakes. And sample size calculation is a way for us to account for it in the planning phase in order to diminish it. Another important factor is that if by instance we underestimate our sample size, we might be missing out on an efficacious treatment, in other words, reaching a false negative result. And if, for instance, we overestimate our sample size, we will be either exposing more people to a hazardous or non-efficacious treatment, or in the case that the treatment is successful, we'll be withholding this treatment from the control group. Not to say about the waste of resources, something that we have to be mindful about, given that we are living in a finite resource world. Okay, so let's go over here just to take a quick look at it. Okay, so now that we've discussed why it is important for us to calculate, let's try to visualize these concepts, right? And then we'll follow on the parameters required to calculate the sample size, right? So imagine that this is our target population, right? So this is the population that we want to apply our intervention after the study is done, right? If we had unlimited resources, we would just measure the intervention in this whole population, comparing it to the appropriate control group, right? But, you know, that's neither ethical nor practical. So we are left with trying to calculate what is the appropriate sample size to better understand the actual truth, right? And while limiting the exposure to the minimal amount of patients as well. So it's interesting for us to understand this concept by looking at a 2x2 table where we look at what is the actual truth, which means that, you know, in reality there is a treatment effect, or in fact there isn't a treatment effect, and compare it to the results that we'll be getting after finalizing our clinical trial. And, you know, we can find that in the clinical trial there was a positive effect of our intervention, or there was no effect at all, right? And hopefully and fortunately, if we perform everything right, we will get into these two squares where we find a treatment effect when there is none, or we find that there is no treatment effect when there's actually none, right? But, you know, sometimes errors can occur. And, you know, so if you fall into this where you find that there is a treatment effect when there's actually none, we have what we call a type 1 error, which is a false positive result. Or we can come to here, which is a type 2 error, where we find there is no treatment effect when there's actually one, and we call it a false negative. All right. So I always like to think about the clinical trial as we are shedding some light into an area of the target population, right? As we can't look at everything, we will be shedding just a light in a small portion of it. And if you see, just by chance, this sample will vary from this one, and will vary from this one, and will vary from this one, right? And the smaller the sample size of our study, the higher the variability between the results, right? And this is called the sampling variability, and it's something that we need to account for. Now, how do we calculate the sample size? Which parameters do you use? Of course, the sample size calculation will vary according to the study design, right? I mean, what is the outcome you're using? Is it continuous? Is it categorical? Moreover, how many times are you measuring this outcome? Are you measuring only once at the end of the study, or are you doing multiple measurements? And this is something that you have to think according to the study design that you've chosen for your clinical trial, right? But one thing that is common to all sample size calculations are three key factors. Remember, we have here the type 1 error. We can estimate it on how to avoid this by choosing the alpha value, and this is typically set at 0.05, but this is a convention, not a rule. And this basically say that we are trying to avoid this type 1 error by this margin. And the other thing that you can see here from the type 2 error is the beta value, or the chance to avoid achieving a false negative result. And this correlates to the power of the study, right? So usually this is set at 80 to 90%, but this can vary according to the phase of the study. And thirdly, we do have the treatment effect. And this is basically us quantifying our hypothesis. We will be looking at this treatment effect and we'll say, well, I imagine that our intervention will affect our population by this much percent. And this can be done usually on three ways: by looking at prior results, if there is one. For instance, You're looking and setting the bar for phase 3 trials based on what you found on a phase 2 trial, right? Or it can be as well by developing a pilot study. There's no literature in the intervention that you're looking for, but so let's develop a pilot study with few subjects just to check how our intervention affects the target population. And lastly, and sometimes most importantly, what is the minimal clinical difference? If you develop a very large study, you can find even the smaller treatment effects. And for instance, if you're looking at the time to effect of an anesthetic, and if the difference is from 60 seconds to 59 seconds, you can develop a trial that will identify this difference. But the question is, should we develop this trial? I mean, is this difference clinically significant in order for us to expose these patients, expose the controls, and invest these resources for us to check what is the clinical difference, right? And now, if we come back here, I mean, just looking at the example of a magnifying glass, right? If we have a treatment effect that is very large, I mean, let's imagine that this is the treatment effect, right? There is a higher chance that even a small sample size will actually identify this effect, right? But, however, if we're looking at something that it's very, very small, there's a high probability that this sample size won't accurately identify this treatment, and sometimes we require a bigger sample size for this. So, just coming back here, the larger the treatment effect, the smaller the required sample size, and the smaller the alpha value, the larger the sample size, right? And the inverse goes for beta. I mean, the larger the beta value, the smaller the sample size. So I'd like to thank you very much for your attention throughout this video. Just to summarize it, we've taken a look at an overview of the landscape of sample size calculation, and we followed on why it is important, and then on common parameters utilized to calculate the sample size. Nowadays, most of the calculations is performed by softwares. You can use STA, you can use SPS, you can use R, and there's even a lot of free online softwares that can do that for you. But maybe, let's not trust those so much. But joking aside, I mean, I think the most important thing for us is to understand the concepts behind it and how and when to apply them. So again, thank you very much for your attention, and I wish you a great start to 2021. Cheers! So just a quick note on sampling variability. I want to perform a test with you. I bought these two different cases of M&Ms, which is something that I believe can be found everywhere in the world, right? So this one, there's 45 grams of M&Ms, and this one, there's 148 grams of M&Ms. So basically, this is 3 times the size of this one. What I want to propose is for us to open these packages and check to see if there is a greater variability in colors from this one, right? So let's go here. Let's open this one here. This is the 148. Well, okay, so you see, here on the right of the pen we have the smaller package, this one here, right? And here on the left of the pen we have the bigger package. And you can see that even though there is a difference between these M&Ms, the difference is a bit smaller. The variability between these colors is smaller than this one. And there's actually quite a striking difference from this one to this one. I mean, if you were taking a look at just this sample here and we would try to infer for the whole population of M&Ms, we would be seeing that there's only a small amount of blue M&Ms, and you know, the majority of them would be yellow and green. And now if we look at this side here, we would be seeing that, you know, there's actually quite a lot of blues followed by greens, then yellows, and it's more evenly, homogeneously introduced. There's not this sevenfold difference from the blue population to the yellow population that you can see here, right? And this is basically that the bigger the sample size, the smaller the variability of it. It's called the sampling error, right? And of course this is due because this the process of packaging the M&Ms is not completely random. It varies from the production factory that they're in, the time of the production, and etc. and all. So they're all just a brief, fun and delicious curiosity.